This is Physics 104A, Chapter 10 homework. Starting with number 13, determine the angular speed in radians per second. So the first one of the Earth about its axis. So to do each of these, you do 2 pi radians divided by how much time it takes. So for part A, that's going to be 2 pi radians divided by a day, but we need that in seconds, 86,400 seconds in a day. And we get 7.27 times 10 to the negative 5th, or negative 5 radians per second. For part B, the minute hand of a clock, it goes around in 1 hour, or 3,600 seconds. So 2 pi over 3,600 seconds. And you get 1.75 times 10 to the negative 3 radians per second. Part C, the hour hand of a clock goes around in 12 hours, so 12 hours times 3,600 seconds, or half of what this was. So you get 1.45 times 10 to the negative 4 radians per second. And part D, an egg beater turning at 300 revolutions per minute. So 300 revolutions per minute, we need to turn that into radians per second. So 1 minute over 60 seconds, 2 pi radians over 1 revolution, and we get 31.4 radians per second. Number 21. We have torque, we have the force. We're going to maximize the torque, let theta equals 90 degrees, pushing perpendicularly. So the lever arm, R, is torque divided by force. 110 Newton meters divided by 90 newtons, so 1.2 meters is the lever arm. Number 23, the mouse on the clock hand. You can see the diagram. I've put it on an XY axis here. Here's the hand, which is 17 centimeters long. The mouse's weight, which goes straight down, is what's applying the torque. So the force is mg at an angle of 60 degrees, because when the clock is, what does it say, reads 10 past the hour. So when it reads 10 past the hour, it's at a 30-degree angle, the minute hand is. So we do torque equals lever arm times force times sine of theta. So the lever arm, R, is 0.17 meters. You have the mass of the mouse. G is 9.8 newtons per kilogram. Sine of 60 degrees, as shown in the diagram. So you should get a torque of 0.07 Newton meters. Number 25, a 2-part question. Part A asks us to consider rotational axis about one of the sides. So we'll do moment of inertia is the sum of every m times its r squared. So I've numbered these points 1, 2, 3, and 4, starting with the lower left hand. So the moment of inertia, if we take each individual m times r squared, for point 1, it's m times 0 squared, because r is the distance from the axis, plus for point 2, ml squared, for point 3, ml squared, for point 4, m times 0 squared. So you add up these terms and you get 2 ml squared. For part B, the axis is going through the middle. So for every one of those points, they have a mass of m. They're a distance of 1/2 L. So it's m times 1/2 of L squared. So each of these points, that's going to be m times L squared over 4. Which you see here, and there's 4 of them, so I have 4 times that, and it comes out to be ml squared. Number 34. Circular saw blade. What's its rotational kinetic energy? Okay, so we consider it to be a disk, I equals 1/2 mr squared. You can solve for I right away and get 6.6406 times 10 to the negative 3 kilograms meters squared. We need omega, so we do the conversion from revolutions per minute to radians per second, multiplying by 2 pi and divide by 60, which gives 366.519 radians per second. Kinetic energy in part A is 1/2 I omega squared, so 446 joules. Average power is the change in kinetic energy divided by the time. It started at rest, so the change in kinetic energy is what we got in part A, 446 joules, divided by 3.2 seconds, so you should get 139 watts. Number 39, a fraction of the solid disk's kinetic energy, or what fraction is rotational if it's rolling without slipping? So here's what we're looking for. The fraction of kinetic rotational over total kinetic, and total in the denominator would be rotational kinetic plus translational kinetic. So you plug in the basic terms. Rotational kinetic is 1/2 I omega squared. Translational is 1/2 mv squared. I see right away I can factor 1/2 out of the denominator, then divide it out of both numerator and denominator, so I've gotten rid of the 1/2s. Now, in this next step, since it's a solid disk, I've replaced I with 1/2 mr squared. In the next line, I substitute that V equals omega r if it is rolling without slipping. So in the numerator, this r squared omega squared, I'm just going to call that V squared. And down the denominator, r squared omega squared, let's call that V squared. So you clean up the denominator. 1/2 mv squared plus mv squared is 3/2 mv squared. The mv squareds divide out. You're left with 1/2 divided by 3/2, or 1/2 times 2/3, and you get 1/3. Number 41. A wheel turns through 2 revolutions while accelerating at 18 revolutions per minute per second. So first we'll do the unit conversions. 2 revolutions times 2 pi gives 4 pi radians. Revolutions per minute per second. So if we write it as 18 revolutions over minute seconds, and then we want to turn revolutions to radians and these minutes to seconds. So 2 pi radians per revolution, 1 minute over 60 seconds. That'll bring us to the units that we want, radians per second squared. So you should get an acceleration alpha of 1.885 radians per second squared. Now part A asks, what's its final angular speed? And it's starting from rest. So we'll do omega squared equals omega naught squared, which is 0, plus 2 alpha change in theta. We already figured out alpha, we already figured out delta theta, so omega squared gives 47.374 radians per second squared, but we want omega, so take the square root of that, and you get 6.9 radians per second. Question B asks how much time does it take? So we'll start with omega equals omega naught, which is 0, plus alpha t. Solve it for time. Time is omega over alpha. And so you should get 3.7 seconds. Number 51. A uniform rectangular flat plane has a mass m, dimensions a and b. Use the parallel access theorem to show its rotational inertia about the side of length b is 1/3 ma squared. Okay, so here's the drawing. We've got a and b. We've got our axis of rotation right through the middle, which is something we can look up in the chart. And we want to find the moment of inertia if the axis of rotation is through this side, this purple line right here. Parallel access theorem says moment of inertia is moment of inertia is moment of inertia through the center of mass, which we look up in the table, plus mass times the distance squared, and the distance is from the axis that we're looking at, the distance between that and the center of mass. So we look up in the table and we get 1/12 ma squared plus mass times, and here's the distance between these two axes, 1/2 of a, so 1/2 of a squared, which is going to be it's going to turn this term into 1/4 ma squared. So 1/12 ma squared plus 1/4 ma squared equals 1/3 ma squared. '52 is the King Air engine. It says to approximate each propeller blade as a uniform rod of length L. So the moment of inertia for the entire propeller, we're going to take it to be 3 times, because there are 3 blades, 3 times the moment of inertia for one rod, which is 3 times 1/3 ml squared, which is ml squared. You're given the mass, you're given the length, and so you should get 15.625 kilograms meters squared. For B, one thing we need is the alpha, the angular acceleration. Starting from torque equals I alpha, we get alpha equals torque over I. We're given the torque, we already in part A figured out I, so you should get 172.8 radians per second squared. We also need to have omega naught and omega 1, the initial and final rotational velocity. 1400 revolutions per minute and 1900 revolutions per minute, you need to convert those to radians per second, and they should get 146.61 and 198.97 for the initial and the final. Then we use this equation, omega final equals omega initial plus alpha t. We solve it for t. T equals the difference of the omegas divided by alpha. And you should get a time of 0.30 seconds. Number 54. Rotational inertia of a flat plane about a central axis. Okay, so we're going to solve for what the table gives us. Here's the picture. So the way you set this up, we have the axis, the central axis right there. You have, here's my x-axis, wherever the axis of rotation is, we're going to call that 0. So it's going to go 1/2 of a to one side, and it's going to be negative 1/2 a down below. The problem recommends divide the plate into strips parallel to the axis. So here's my little strip, one of them with a width of dx. Moment of inertia is the integral of r squared dm. Now, since we're doing the x-axis, we can just say it's the integral of x squared dm. We want to replace dm with something related to dx. So we're going to consider this, that the area of a strip as a proportion to the area of the entire plate is equal to the mass of a strip divided by the mass of the plate. So we know the area of the strip, it's a thin rectangle of length b and width dx, so that's going to be b times dx. The area of the plate is AB. The mass of a strip is dm. The mass of the plate is capital M. So we can solve for dm. The b's cancel out, and you should get m over a times dx. Now we're going to take this integral, that I is the integral of x squared dm. We're going to replace dm with m over a dx. And so we get this integral. I equals the integral of x squared ma dx. And we can add the limits of integration. I do that in the next step. All the constants, we can put them to the outside of the integral. So m over a, I put that to the outside. Now, with more space, I've put the limits of integration. We're integrating from negative a over 2 to positive a over 2. That's the width of the door. What's left inside the integral is x squared dx. So we integrate. Integral of x squared dx is 1/3 x cubed, and I've thrown the 1/3 out to the side because it's a constant. So now with x cubed, plug in those limits of integration. So it becomes a cubed over 8 minus negative a cubed over 8. So on the outside of the integral was m over 3a times, and in the brackets that becomes a cubed over 4. So we get 1/12 ma squared. Number 61, the hollow ball. Rolling down the incline, and we want to find, after it's gone a distance d, what's its velocity. So as I draw a picture here, this is actually going to be a conservation of energy problem. We have the ball at the top, the ball at the bottom. It's useful to know that h equals d sine theta, just from this right triangle. Conservation of energy says the energy at the top equals the energy at the bottom. So energy at the top, it's at rest, and so we're going to take that all to be its potential energy, mgh. And that's why it's useful to know this trig over here, that h equals d sine theta, because we need this problem in terms of d. Energy at the bottom is going to be all kinetic energy. We need the translational kinetic energy plus the rotational kinetic energy. So 1/2 mv squared plus 1/2 I omega squared. mg, and now I've made the replacement that h is d sine theta, equals 1/2 mv squared plus 1/2. It's a hollow ball, so 2/3 mr squared times omega squared. Now, r squared omega squared is v squared, so we're going to make that replacement in the next line. Also, you can see in this line I've crossed out, you can factor out m out of the right-hand side and divide the entire equation by m, so the mass of the ball goes away. What we're left with is g d sine theta equals 1/2 v squared plus 1/3 v squared. The 1/2 plus 1/3 is 5/6. So we have 5/6 v squareds. Move the paper up here. Okay, gd sine theta equals 5/6 v squared. And now we solve for v. So v squared equals 6/5 gd sine theta. So take the square root, and you get v as the square root of 6/5 gd sine theta. And that's all for chapter 10.